30 at 11. Did he? Did he? Oh, can't stop there.
We've all been there. For 2,000 years, we thought that in order to keep an object moving, you had to push it harder or keep pushing it. And that's honestly how we thought motion worked up until the 1600s. So I'm going to call it the old way of thinking. In order to keep an object moving, you have to apply a force onto it. And if you take the force away, the object will stop. Just like Tiger's putt on the 11th green at the PGA Championship this year. And it wasn't until these three guys kind of came up with one big idea. These three, they're sort of the big three of physics. Galileo, Descartes, and Newton. They came up with this idea that what if we've got this entirely backwards? You know, you've been to the supermarket and you push your shopping cart along and you let it go and you try and aim it for the shopping cart carriage place. And if you don't push hard enough, it'll stop before it's supposed to get there. Or if you're sliding a box on the floor and you let it go, it's going to stop. And in order to keep it going, you have to keep pushing it. But these three guys sort of had this idea that what if we've got this all backwards? What if we've been thinking about this the wrong way? What if everything is supposed to keep moving and the reason it doesn't is because there's a force already on it? And that was sort of this revelation because nobody really thought of things that way because that wasn't anybody's experience. And even with you and me, my experience, I have to keep pushing an object to keep it moving. But the new way of thinking sort of got broken down to something a little different. So let's take a box and we'll push it that way. And we'll keep that box on a rough surface. And as soon as you let it go, that box will stop. But what if instead of having it on a rough surface, what if we had it on a little bit of a smoother surface? And you push it and you let it go. It'll take a little bit longer for it to stop. And what if we put it on an even smoother surface? Let me get on a line here and maybe a sheet of ice that's really, really smooth. And you push it. And the idea is that box will take even longer before it stops. So what their idea was, sort of between the three of them, was that maybe there's some force acting against things that are moving. And that sort of changed the way that we thought about things, that instead of keeping forces on objects to keep them moving, you kind of have to remove forces from objects to keep them moving. So I tried hard to write before and it just didn't work. So bear with me. I'm not going to put you through writing it. Type it. So the new way of thinking became this idea of removing up forces from objects to keep moving and keeping outside net forces, which we'll talk about in a second, to a minimum to keep an object's motion constant. So under the old way of thinking, if you put a force on it, that's what keeps it going. And if you take that force away, that's what makes it stop. Whereas the newer way of thinking was if I if I want an object to stop, I just leave it alone. And if I want an object to start moving or at least change its motion, I have to push it. So Newton's first law comes along, and I'll paraphrase it with the following. An object at rest will remain at rest unless acted on by an outside force. And the same way, an object in motion will remain in constant motion unless so an object will remain at rest unless acted upon by an outside force, and an object in motion will remain in constant motion unless acted upon by an outside force. So that's Newton's first law. And now we get to talk about what this idea of a net force is. And I think the best way to do that is to basically just draw it out for you. So if I've got an object, and let's leave it in space. So let's make a box. We'll put it, or better yet, a circle. There we go. We got a circle, and we're going to put it in space. And if it's in space, and we're talking deep space where there's no gravity, no nothing near it, there's no force acting on it. But now let's take this circle, let's take this sphere, this ball, and let's move it to the ground. Move it to the ground, and let's make a ground here for it to rest on. So sure, that looks like it's on the ground. Now all of a sudden it's on the ground, and we've got some forces on it that we can actually describe. We can talk about gravity being a force that's down. That's Fg, also known as the weight force. And we could talk about normal force being going up. And I'll write that down. We call that the normal force, or the contact force between the ball and the ground. And what a net force is what you get when you add these two forces. So Fg plus Fn equals F net. In fact, a net force is F net is the summation, if you remember this Greek letter sigma, of forces on an object. So when you want to know what the net force is, all you have to do is look at the object and add the forces together. And just like in two-dimensional kinematics, if you have forces only in one dimension, you can organize them by adding them together because they're collinear. But if you have objects in two dimensions, let's say we are pushing this object. So now let's call that applied force, F-A-P-P, applied. And let's say this ball is experiencing some friction. So I'll call that F for friction. That's what we call so those are two other forces that are sort of in different dimensions than the normal force and gravitational force. You can actually add the forces together in both the x and the y dimensions. So the normal force and the gravity would be in the y dimension, and the applied force and the friction force would be in the x dimension. So a first law situation is what happens when the net force equals 0. So basically, when there is no net force on an object, so the F net equals 0 newtons. And that would be what we call statics. So F net equals 0 newtons, and that is what we call something that is static. Okay, so I'll describe things in class about statics. An example of a static object is a picture frame hanging on the wall. La da da, little mountains, little sun, little river. Sure, that looks like a river. And it's hanging on the wall because you got a nail And we've got forces acting on this, and what we're going to be doing in class is describing what those forces are. So we got a nail in the wall, we got some string holding the picture up. Another example of a first law situation would be a car driving on the road. So there's my car driving on the road, but it's in cruise control. So now I've got different forces acting on it, but my car is not accelerating. It is going under constant velocity. Okay, so for a picture frame on the wall, I have no velocity. For a car undergoing constant velocity, there is a velocity, but it's not changing. Both of these things are not accelerating. And that is the magic for what makes a first law situation. You cannot have an object that is accelerating and have it be a first law situation. So in order to do these, all we're going to be doing is a lot of something called a free body diagram. And a free body diagram is a picture, hence diagram, where your object is represented by a dot. And all of the forces acting on your object are going to be represented by arrows. So you can have a force going up, you can have a force going to the right, you can have a force going down, you can have a force going at any angle. You just have to know what the different names of the forces are, and we would label those forces with an F whatever, pick a letter, Fg for gravity, Fn for normal force. But those forces are represented by arrows emanating from the middle of a dot, which is what represents your object. So if I had a ball, again, sitting on a table, my free body diagram would be a dot with a ball, the ball's weight represented by the force of gravity, and the normal force from the table represented by Fn. So I hope that sort of introduces you to this idea of what Newton's first law is, where it came from, why we have it. And what it really boils down to is Newton's first law goes against everything we ever thought about motion in the first place, that we had to keep pushing objects. These big three, Galileo, Descartes, and Newton, came up with this idea that, well, maybe if we have an object, it doesn't really want to be accelerating, and the only way that we do accelerate is by actually giving it a force. So even going back to that Tiger Woods putt, that ball wanted to keep going. Once Tiger Woods hit the ball, he gave it a force, and therefore it started moving. The thing that slowed it down, evidently too much for it to make it in that cup, was the force of friction, which is a force that opposes motion. So again, we have this new way of thinking where things don't want to speed up or slow down. They want to keep going the constant speed, but it's other forces that cause them to slow down. So Newton's first law came from that, where he basically says an object will stay at rest unless we actually push it. And an object that's already in motion will want to stay in motion unless there's another outside force involved. And then we went into talking about what net forces are, and that's what happens when you add all the forces. And if they all add up to zero, then you have a first law situation where the object does not want to speed up, it doesn't want to slow down, and it doesn't want to accelerate. It doesn't want to change its motion. So any of these first law situations apply to a net force of zero. And then I gave you a little bit of a brief overview of how we describe these things using appropriate physics jargon with free body diagrams. So I hope that sort of helps set you up.